of Green's theorem. All right, so we had the outward flux was equal to a double integral of the divergence. And so another way we can generalize this is if we go up a dimension, and instead of looking at the outward flux across a region, so we had, Green's theorem. We had our curve C, we had our region R, and we were looking at the outward flux from this region across C. It was a double integral over the region R of the divergence. Right, so that was 2 dimensions. We can go up a dimension and then talk about looking at the flux across a surface. So I know one of you, I forget who it was. It might have been, was it you, Ryan, that was talking about AP physics and Gauss's law? Yeah, okay, so this is the kind of stuff I was talking about. Okay. And we might not get to it today, but tomorrow we'll actually go through sort of a proof of Gauss's law about electromagnetic flux. But this is what we're doing now, because the way we generalize this is instead of looking at a simple closed curve bounding a region, we're going to go up into 3 space, and we're going to look at some solid, say Q, and the boundary, some surface S. And we're going to look at the flux across S. So if I look at the flux across S, assuming this is a closed surface, so we'll put a circle around that to indicate it's a closed surface. We'll get the outward flux, the surface integral flux. Welcome in, Adam. That's going to be then the triple integral over Q of the divergence of F. And once again, tomorrow we're going to spend 10 or 15 minutes kind of going through all these big theorems and kind of talking about how they're all the same. But notice we've got it. We're integrating over this whole solid a divergence, which is essentially a derivative. And the result of that is having an oriented sum along the boundary of it. Okay, so this is, once again, this is just another incarnation of the fundamental theorem of calculus. All right. So once again, how do we use this in this course? We're going to use this as an excuse to go back and review how triple integrals work and how surface integrals work. Okay. All right, so there's the divergence theorem. Example 1, here's this field 2x, z, 3y. I think, was this the same one yesterday? I think it is. I'm really focused on making sure people know how to set these up. And this might be a good help for some folks. If you haven't turned in your homework yet, there's an example we should get to today that'll help you with that. So there's 2x, z, 3y. The q be the portion of yeah, this doesn't make any sense. Be the portion of the plane Q be the portion of, oh, I'm sorry, no, that's right, the portion of quadrant 1 bounded by this plane. So remember, Q is going to be a solid. All right, so if you go to graph this, and if memory serves, this is the same, isn't this the plane we had yesterday? I think yeah, this is the plane we had yesterday. So here's what Q is. What kind of shape is that? So Q is going to be a what? You've got this front, got this front-facing triangle along with all the sides. So this is a tetrahedron. Okay, so Q is this is a solid. Right. We want the outward flux of F across the boundary of Q using flux integral. So if Q is a solid, it's a tetrahedron, then how many pieces parts is its boundary? Well, let's count. So we're going to have this surface here. We'll call that S1. So we got S1 as part of it. Yeah, right. There's 4 faces. So we'll call that one S1. We'll call this S2. That would be the projection into the XY plane. And I don't know. We'll call this S3. That's the projection into the XZ plane. And then we'll call the back S4. Oh, I got you, Zeron. Yeah, no worries. So yeah, so this, and we have to think one dimension up, because I mean, to be fair, that's what we were talking about yesterday, but we're one dimension up. So Q is this solid. It's a tetrahedron. It's the portion of quadrant 1 that's cut off by this plane. Okay. So S1 is going to be the portion of the plane 3x plus 2y plus 3 plus 2y plus z is 6 in the first octant, and this should be octant in the first octant. Okay, so that's S1. So I need the flux of F across S1. Okay. Now, the flux we want is outward from the solid Q. So if I'm looking at the outward flux of this field, so I kind of have 2 options. All right. Option A is that way. Option B is the other way. So this would be option A, this would be option B. Which of those directions is going to be outward from Q's perspective? If I want to see how much is getting out of Q, that'd be option A. Very good. Now, so if I look at this, I'm going to, once again, to evaluate the flux integrals, going back to what we did last week, I've got a function of x, y, and z, right? I'll have to pick one of those. So if I'm going to say solve for z, which is easy to do. So if I think of this as z is 6 minus 3x minus 2y, if I think of that as my f of x, y, then outward is going to be synonymous with what direction? Is this vector going to be pointing in the up direction or the down direction? Do I want upward flux across S1 or downward flux? Yeah, upward flux. So that's going to be upward. Are there any questions on how we're deciding the directionality of this vector? So we're looking at stuff coming out across the boundary, out of Q. So out of Q, we would have a positive z component. So if I solve this surface, z as a function of x and y, I want the upward pointing normal for that one. All right, so let's do it. We need n up. Per our recipe we learned last week, that's a minus fx minus fy positive 1. And I believe we used this vector yesterday for something, because minus fx would be what? 3. Minus fy would be what? 2, and then 1. So that was the bad joke. We're counting down to the end of the semester here. All right, now I go look at my field, f of x, y, z. And the field is 2x, z, 3y. But on the surface on S1, the surface is given by z equals 6 minus 3x minus 2y. So I would have 2x, and then the z would be 6 minus 3x minus 2y, and then the 3y. So this gives me the field as a function of x and y. So I've got my normal vector, I've got my field. So the flux I want would be a double integral over r of f dot n up dA. So now we calculate that dot product. See what we're working with here. And we go back the end of the first week of class. Take that dot product, multiply the x components, multiply the y components, multiply the z components, and once we're done multiplying them all, what do? Add them up. So I got the 2x times the 3, which is the 6x plus. I've got all of this times 2. So that's going to be 12 minus 6x minus 4y. And then I've got the plus 3y. There we go. So when the dust settles, what am I integrating here? What happens to the x's? Yeah, they're gone. And I got a 12 in there. Minus how many y's? Y. Okay? Now, how do I get the region R? So I go back, and I made a choice here to solve z as a function of x and y. So the way I get my region R is I got to project S1 into the xy plane. So I'm going to project S1 into the xy plane. And so I go back and think about what we talked about at the end of the second week of class. That's my S1. What's the quick way to figure out what this projection is going to be? Yeah, just fire up z equals 0. That's your xy trace. This would be 3x plus 2y is 6. So you got your x-intercept 2, y-intercept 3. That's my region R. And so now we can go ahead and set up this double integral. All right. So we need to pick an order here. First off, is this a candidate for polar coordinates? Is this something I should switch over to polar? Because that's always an option with double integrals. Yeah, you could, but it's a triangle. If this were like part of a circle, then definitely, but it's not. So we're going to stick with rectangular. Does the order really matter? dx, dy, dy, dx? So let's just pick one. What do you want to do? dx, dy? All right, we'll do that. So dx, dy. If we're doing dx, dy, that means we're going to chop the y up from constant bounds. So we're going to chop up the y. We're chopping up the y-axis. It starts down here at y equals 0 and ends at y equals 3. And now for a fixed y, I got to figure out what the x is running between. So it starts here on the y-axis, aka x equals what? Zero. And then it goes out to this line. And what I need to do is to figure out for a fixed y how far the x goes. So I got to solve that for x. Yep, good. 2 minus 2/3 y. Okay, there we go. Boom. 2 minus 2/3 y. So let's go through and work through this integral. So integral 0 to 3. Let's integrate this. What's the integral of this with respect to x? So 12 is a constant. Integrate 12 with respect to x. What do you get? 12x. And y is also a constant. So when you integrate that with respect to x, you just get xy. This is from x equals 0 to x equals 2 minus 2/3 y dy. And once again, I want to go through this because I think it's been a while since we actually went through one of these that didn't just simplify to an area. So we got 12 there times a 2 minus 2/3 y minus x times, it's not x, but 2 minus 2/3 y times y. And when you plug in x equals 0, what's going to happen to both of those things? That just zeroes out. All right, now we're left with a little Calc 1 integral here to do. So this is equal to the integral from 0 to 3. Let's go ahead, distribute here. You got your 24 minus, how many y do I get from that? 8y minus, now I've got 2y, and then what happens here? I got a minus and a minus. That's going to be a what? Plus 2/3 y squared dy. We can simplify that a little bit. 24 minus 10y plus 2/3 y squared dy. And now we integrate it. Now we're integrating with respect to y. So this is a, going back to your Calc 1. Toss that in. What do you get there? You get 72. Oops, not 70. 72. Minus 45. Plus, now when you plug in that 3 cubed, you get a 6. And then when you plug in 0, you just get a bunch of zeros. So when the dust settles, what's the outward flux? Across the upward flux, rather, across S1. 33. That sounds right. All right, so that's the flux across S1. So the upward flux across S1 is 33. Okay, now we just got 3 more sides to do. So let's go back. And what did we call it? I called S2 the bottom. So S2. So let's look at S2. All right. So what is S2? Well, how would you describe S2? S2 is the xy plane. What's the equation of the xy plane? Yeah, z equals 0. So S2 is z equals 0, but it's the part of z equals 0 that was the region over which we integrated last time. Right? So this is the region we integrated over last time. That was our projection of S1 down into the xy plane. But S2 now is part of the boundary. That's its surface. But we know, what it looks like here. That's your 3x plus 2y is 6. We know that. So we know that's 2 and that's 3. Right? This is S2. Now, from S2's point of view, which direction is outward from Q? Is it the up or the down? It's going to be the down. All right, so I can do the down Well, you might guess what it is, but if I wanted to go through just to show you the formula's consistent here, fx and fy are both what? It'll be plus plus negative 1. If f of xy is 0, the partial derivatives are all what? 0. Okay. And if I look at my field is 2x z 3y. But if I'm on the plane where z equals 0, my field of xy is just going to be 2x 0 3y. You follow? And now if I figure out what I'm integrating, I go through the old dot product. Because the only direction that matters here is the z direction, I'm just going to get negative 3y for that dot product. So f dot n down is minus 3y. And so the flux is going to be the double integral over r of minus 3y dA. And r is the same as the last part. Because it's the projection of Q into the xy plane. So we can just go ahead and use the same setup we had before. We had y running from 0 to 3. We had x running from 0 to 2 minus 2/3 y. We've got a slightly different integrand, dx dy. And now we'll go off and integrate that. So everybody cool with why this is the same? S2 is the bottom of the tetrahedron, so it's the projection into the xy plane. That means it's the same region. But the field down there is different because it's z equals 0. And the normal vector is different because it's the downward normal. Everybody okay with getting this set up for this integral here? All right, so we start integrating here. I'm going to have the integral from 0 to 3. What's the integral of minus 3y dx? Minus 3yx, good. This is from x equals 0 to x equals 2 minus 2/3 y dy. 0 to 3. We got toss in the top, minus 3y. 2 minus 2/3 y. Minus plugging in 0 gives you 0. Integrating 0 to 3. Distribute. We got a minus 6y. And then what would this be? A plus what? 2y squared. All right, so now we integrate this, just like the old days. What's the integral of minus 6y plus 2y squared? Minus 3y squared plus 2/3 y cubed. Good. And this is from y equals 0 to y equals 3. So it looks like we're getting a negative 27 here. Plus a what? An 18. So a grand total of -9. Now, once again, when you have a negative outward flux, it means that the net effect, is there more stuff going out the bottom or coming up through the bottom if it's a negative outward flux in this case? If the outward flux is negative, that means that there's more stuff doing what? Coming in or going out? Yeah, coming in. All right, so where did I put this? I was keeping a record of these things. The downward flux across S2 is -9. Okay, so there, that's done. All right, 2 more to go. All right, S3. S3 is the projection into the XZ plane. So S3 would be the projection of Q into the XZ plane. So what's another name for the XZ plane? Y equals 0. So I have y as a function of x and z. That's 0. And which direction do I want? Do I want the left or the right here? Which of these directions would be out as far as Q is concerned? The left. So I want the leftmost normal. So I want the left one, which we talked about last time. So if I want the left normal, I want a -1 for the y, which means I'd have a positive gx and a positive gz. Really doesn't matter though, because if g is 0, the partials are also 0. All right, so once again, hopefully no surprise here. It's -1 is the, or minus j hat there, that vector. Now I look at my field. Once again, the field is given by 2x, z, 3y. But if I'm on the plane y equals 0, I can get my field as just a function of x and z. Two x z times 0. And now I dot these vectors. And f dot n is -z. So f dot n left is -z. So the flux I want is going to be the double integral over r of -z dA. And now I got to figure out, how do I figure out the region R? So this is the left face of the tetrahedron. So I'm going to project Q into the XZ plane. So we're going to let y equal 0. Yep. So the 3x plus 2y plus z is 6. We're going to let z equal 0 and project that. 3x plus z is 6. And that's our region R. Okay. Once again, any questions on how we're figuring out what the region is? All right. So the flux is going to be a double integral. I got -z. I got to pick an integration order. What would you pick your order to be? You want dx dz or dz dx? Dx dz? All right. So if I do dx dz, then I'm chopping the z up between constant bounds from where to where? Zero to 6. And now for a fixed z, I have to figure out what the x runs between. So the x here, that's the z-axis. That's x equals what? 0. And then that is x equals what? So 2 minus 1/3 z. So there you go. All right, now I go through into the integration here. What's the integral of minus z with respect to x? Minus zx from x equals 0 to x equals z minus 1/3, 2 minus 1/3 z. So I'm just going to have minus z times this. Distribute that negative z through. I got a minus 2z plus a 1/3 z squared. dz. And now we're back to the old days. What's the antiderivative of minus 2z plus 1/3 z squared? Minus z squared plus 1/9 z cubed. And this is going from z equals 0 to z equals 9. So this is going to be a minus 81 plus 1/9. Well, let's see here. I'm sorry, we're plugging in z equals 6, not 9. I'd have 6 cubed, right? So 6 cubed, that's 3 times 3 times 3 times 2 times 2 times 2. 2 of those would get canceled out there, right? So that would be gone. I'd be left with what? 24. So minus 81 plus 24, what's that give me? Excuse me. Negative 57. So that would be your flux across that one. I think we did something wrong. Yes, I plugged the, yeah, it was, remember I had a 9 up there. There we go. All right, now what do we got there? That's a negative 12. Yeah, thank you. Okay, that's looking good. All right. Okay. So now we got one more to do. So now let's put that in there. The left flux, I don't know, leftward flux across S3 was negative 12. Right? That was right. Negative 12. Yep. Okay. All right, one more. So S4 is now the back of Q. So it's the projection of Q into the YZ plane. YZ plane, aka what? X equals 0. So we got our X as a function of Y and Z. And so if we want the backward normal, X would be -1, and then you'd have an HY, HZ. But since h of xy equals 0, not surprisingly, what's my vector here? -1, 0, 0. Let's take a look at what our field is. So the field is 2x, z, 3y. But in the when x equals 0 in the yz plane, f of yz is what? So look what happens, folks. What happens when you go take that dot product? Everything zeroes out. So f dot n back is identically 0. Right. That means, I'll leave it to you, because we want to wrap at least up one example before we're done. You can go ahead and graph that field and see what's happening with that field in the YZ plane. Right. If you look at it here, you can see what's going on. When x is 0, you've got no movement in the x direction. So the field should just be sitting, right? All the arrows should just be pointing in the YZ direction here. Okay, so it should look like some kind of circulation happening in the YZ plane. Does that make sense? So that means that the flux is 0. Right? Because when you integrate 0, you get 0. You can't get something from nothing. Oh, that's physics. Sure, thermodynamics, right? That's one of those things. And then the backward flux across S4 is 0. So you add all those up, and you get the total flux is what? You got things coming out across S1, but then you got stuff coming in from S2, stuff coming in from S3. Nothing's happening on S4. So you get 33 minus, what, 21? So that gives you a total of what? $12. So there's still more going out than coming in. You follow? You got stuff coming in across, the net effect across S2 and S3. Stuff's coming in. Stuff's going out around S1. There's more going out than coming in. So the outward flux is positive 12. All right? Okay. Good review of flux integrals. Check your answer using the divergence theorem by calculating the corresponding triple integral. Okay, so the divergence theorem says I can get the flux by just doing one triple integral over the divergence. So we got to figure out the divergence of f. So we've got our partial with respect to x, partial with respect to y, partial with respect to z, dotted with f, 2x, z, 3y. And we just do this as any other dot product. Yeah, 2 plus 0 plus 0 is 2. So that means I'm just integrating 2 dv. Now, if you integrate 2 dv, that's just going to give you 2 times the what? So what happens if you integrate 1 dv? What's that? That's just going to give you the what of q? volume. This is just giving me the volume of Q. Now, Q is a tetrahedron. So, I mean, that's 6, that's 3, that's 2. So it's got a height of 2. Excuse me, a height of 6. Well, I guess you could have, depending how you look, at a height of 6. The area of the base is 1/2 2 times 3, which is what? 3? And the height is 6. So anyone know the volume of a tetrahedron? I think it's 1/3, right? 1/3 the area of the base times the height, right? So it'd be 1/3. So it'd be 18. So it'd be 1/3 times 3 times 6. So that's going to be 6. So 2 times 6. Voila, it's 12. How neat is that? So it works. It works. Okay, there's divergence theorem. All right, tomorrow we'll look at this field over this. Now what's happening here? What is this? I got x squared plus y squared plus z squared. Down here it's equal to 1. Up here it's equal to 4. So so what I'm doing, I'm looking at the volume between spheres. Right? So I've basically got a sphere with a smaller sphere. So we're looking at that. Looks kind of like an avocado, but okay. So we'll go through and do the flux integrals. And this is analogous to, remember when we did Green's theorem and we had like a hole in the middle? Remember that? This is the three-dimensional version of that. We'll do that tomorrow. Do some parametric nonsense with that. And then we'll talk about example 3. This is the one, Ryan, this is the one I think. I might have sent you a video on this one. Are you doing that for your project, Ryan? Not sure? Okay. Well, we'll talk about how this would work. Considering, okay, no, that's cool. We'll talk about this one. But, you know, we should wrap stuff up tomorrow. And then have Thursday and Friday as work days. Okay? Or, depending on what you're actually working on, pun intended, it would actually be flux days, right? There'll be flex days, flux days. All right, folks, as always, I appreciate you tuning in. Enjoy the rest of the day. The weather looks like classic December weather. So if you're out and about, be careful. And we'll see you here tomorrow.